Okay, so let's get started today. TA, Prashant, if you're online, please remind me if there's any online questions. Thank you everybody for understanding that I'm moving today's lecture online because my whole family is going through something that, we are all kind of sick. So luckily we have Zoom to the rescue that we will not be able to, we will not delay our actual material. So today will be the last lecture I'm going to talk about regarding visualization. So today we're actually going to talk about principles of data visualization. So if you recall the 3 lectures, we have the first lecture on visualization. We kind of talk about how to use Jupyter Notebook and Python libraries to create some of those simple data visualization. The second lecture, we talk about how visualization can be used to help understand and mitigate biases in word embedding, which is a particular application of data visualization to help machine learning interpretability. And today I'm actually going to go back to discuss some of those principles over data visualization, some of those design guidelines when you think about data visualization. Okay. So there is a quote that is motivate the study of computation, which is the purpose of computing is insight and not numbers. And this is a pretty straightforward statement, and it's not really that debatable because we all understand, just presenting number does not equal to insight. This same sentence could also be updated to discuss data visualization. So specifically, we can replace the word computing by the data visualization and then the picture numbers by pictures. So what this sentence means, the purpose of visualization is insight and not pictures. So very much, creating a good looking picture is definitely not the whole story in terms of data visualization. It's more about what is the insight that the visualization could communicate. So specifically, if I were going to present one definition of data visualization, it is a process that transforms most times abstract data into interactive graphical representation for the purpose of exploration, confirmation, or presentation. So of course, depends on the type of visualization you create. The visualization also target different audiences. For example, in the last lecture, when we talk about using visualization, especially interactive visualization, to understand and mitigate word biases, the audiences are actually natural language processing experts and people who work with machine learning models that employ word embeddings. So for them to understand and explore biases, but also the interactive tool we developed was also targeting towards NLP novice users to initially understand the existence of biases in word embeddings and to understand some of those bias mitigation algorithms that is in the literature. So in short, there are 2 types of audiences for the interactive visualization for word debiasing. One is NLP expert and machine learning expert, and one are, in some sense, we call pedestrians, who are, novice users to try to understand some machine learning concepts. So when we talk about visualization, we are going to sort of quantify the quality of visualization. And what we consider as good data visualization will touch base over one of those many aspects. Number one is the visualization would make data more accessible for people to understand. It also typically combines strength of humans and computers to enable the discovery of insights and also to enable communication of information. So specifically, when we think about why we want to create visualization, the first one is communication. right? So you actually are now seeing a lot of those visualization over online media outlets. For example, New York Times, Washington Post, or have a very specific data analysis and visualization branch where they're trying to convey complicated data or complicated situation through visualization. For example, over the pandemic, you see multiple different plots over the trend of the pandemic. If you actually look at even for our local news, the Utah pandemic numbers, there's usually a plotting of the pandemic trend to guide people over planning their daily life surrounding those pandemic numbers. So the idea is to communicate. Also, during election, whether it's local or national election, you will see a lot of sort of communication over the numbers as the election polls, and most of those are presented in the form of visualization because they are easier to communicate than numbers alone. The second type are actually what's called exploration. So sometimes, we don't really know the specific insights we're after. So very much the questions is not well defined. So we're using visualization to explore the data. For example, understand the structure of a terrorist network or which drug can help a particular patient. We don't really know the exact answer, and oftentimes we don't even know the right question. And the sort of the goal of it is to try to define the right question and discover the corresponding results. Okay, and this in comparison with communication is oftentimes we know the data we want to communicate and we want to create more effective means for communication through visualization. So, for example, this is actually sort of on the right-hand side, you see sort of a plots where the x-axis are the dates between the year 2007, 2008, up until 2010. And then the idea is try to visualize the US job loss from December 2007 to January of 2010. So on the right-hand side, the idea is that I already know sort of the job market data set. And then the idea is to try to communicate those through visualization. On the left-hand side, you see what's called a parallel coordinates plot, and it's actually slightly more involved parallel coordinates plot. And each of those columns you see corresponding to a dimension of my high dimensional data set. And each line that connecting all those columns are actually corresponding to one high dimensional data point. And through parallel coordinates plot, the goal is to try to explore the data set. Okay. And then in a way of thinking about visualization, remember, when we are thinking about insight, this insight is typically generated by the human, not the computers. So if we're actually thinking about the goal of visualization, we can think about the two axes of sort of what we call ability matrix, where the x-axis is corresponding to the performance of a human being. Things like, at high performance, a human being, we're very good at cognition, very good at common knowledge and creativity. We're reasonably okay in terms of prediction, diagnostic, and planning. And then the y-axis is corresponding to the performance of a computer, which specifically is very good at memory in terms of data storage. It's very good with numerical computations. It's relatively good with search and finding as well as planning. And somewhere in between are both human and computer are both capable of performing some form of logic. All right, so the visualization is really trying to strike a balance of utilizing the capability of a computer, but also the capability of human in terms of insight generation. All right, so people often asked, going back to the original motivation of visualization, why can't we just use statistics to convey, my data set? And, and then the motivation for visualization is, a picture is worth 1,000 words, or a picture is worth 1,000 numbers. I want to push forward to that is that if you think a picture is worth 1,000 words, you have to make sure that picture is the right picture. So here is a quick example. I'm showing sort of a bunch of columns of data. Each column, if you see this, they have actually varies quite a bit with the X and Y. But in case you are curious, what is the statistics? All those each columns actually have the same statistics. Now, this is what's called the famous the quartet picture, which you see this plotting of those 4 groups of data. They appear to be very different visually, but they actually share identical statistics. In fact, people push this even further to show that, this is a paper at the CHI conference, which is a human-computer interaction conferences, which basically people are able to generate arbitrary data set with the same statistics. So in this case, you see a picture of a dinosaur, and on the right, it shows sort of mean of X, mean of Y, standard deviation, and correlation. And what you can see is that I can actually vary the visualization of the data, maintaining the exactly same statistics. Okay, so what is the first message? The first message is, well, a picture is worth 1,000 words to show the differences over the data. You can have data with the same statistics, but very different visualization. Now, what I want to drive home today is that visualization is essentially human data interaction. So human plays a very important role both in visualization design and visualization interpretation. So if we think about the role of visualization in the data science pipeline, you start with data that are coming from the real world, and you move on into collecting of this data, the processing, and then the cleaning of the data. If you recall, we spent some time talking about data wrangling. And then after we have the clean data, one of the tasks we want to do is exploratory data analysis, meaning that we don't know exactly the type of question we want to ask. Even if we do, we don't know exactly the type of result we are expecting. So that is exploratory data analysis. Of course, once you have the clean data, another pipeline you might follow are applying machine learning models, algorithms, data analysis algorithms, statistical models, and so on. And once you perform those data analysis tasks, the next thing you want to do is to communicate the results to the user. And that's where visualization comes in, is through communication and report of the findings. And once you have presented the result, the analysis results through visualization, we can use those for decision making. And of course, all this pipeline kind of feedback after the first rounds, you can feedback again going to the initial start of the pipeline. So just looking at this picture, again, there's 2 major roles visualization plays. One is exploratory data analysis. The other one is communication. So why do we really emphasize the role of human in creating and interpreting visualization? Is in some way that visualization is actually leveraging human capabilities, specifically in terms of pattern discovery. If you ever recall a visualization, for example, people show you a clustering result, it's usually through visualization because human mind naturally try to group items together when they are positioned close to each other. Similarly with outlier detector. Again, going back to the example of the pandemic, when we are keeping track of, say, the state of Utah pandemic numbers, what human is very good at is looking at, sort of the COVID number patterns. And specifically, in recent weeks that the COVID-19 cases has been declining. And when we shown a visualization, we can quickly pick up the current pandemic trend. The second type of thing for human capabilities is we also very good with contextual knowledge. And we are very good at sort of in a way to explain the patterns we find and come up with reasonings. And then we also generally have some expectations for the data set that we are analyzing or visualizing. And finally, that humans are essentially the people who are going to learn and take actions and make decisions based on the information that is communicated to us through visualization. And another side that even though humans are very capable in all those different sort of tasks, we also have to keep in mind to design for the particular audience, the humans, and take into consideration human limitations. So in other ways is that not everything can be drawn or can be read. So on the right-hand side, what you see is a very typical visualization, a naive visualization of, say, a social network. When the social network became really large, that you oftentimes, if you just employing naive visualization, you're going to see essentially what we call the hairball. Doesn't matter how complicated the hairball is, the actually only information that a human viewer is going to collect out of this visualization, it is just a hairball. And then there's no insight that can be derived from it. Okay. And then the example on the left, even though you try to show some visualization, but there's no connection between sort of different cluster you try to do with the underlying visualization. So even though visualization can be very powerful and effective, you need to figure out what is the right visualization to use. And the first thing we want to talk about is actually what's called change blindness. Is a phenomenon of visual perception that occurs when a stimulus undergoes a change without this being noticed by its observer. So if you actually watch this video, a guy was asking for directions, and the gentleman wearing glass and white beard is giving the directions, and then in this particular case, he just switched to another person, where the person who's giving the instruction didn't even notice. This is one example of a change blindness, but this can also happen quite a bit when you actually design visualization. Okay. Yeah, so even though the person he's talking to is a completely different person, he didn't even notice. So if we go back to history, one of the first visualization actually has an interesting story behind it. Back in 1854, in London, there is a specific outbreak. And at the time, people actually think that outbreak has a lot to do with bad air. And then at the time, people don't know about the concept of germs. A particular physician, John Snow, reminder of isn't that Jon Snow? Well, okay, I was thinking about Lord of the Game of Thrones, but anyway, a guy, Jon Snow, had a theory that the germ actually originate in the water system. So he specifically studied the patterns of outbreak and identified a specific water pump that is responsible for the outbreak. And then he persuaded authorities to disable the pump by removing its handle. So this is arguably the first or earliest and most powerful use of data visualization. So this is a picture created in 1854. This is sort of a map in the local, in sort of the streets of London. And then what you can notice here is where that orange arrow is where, in the middle of the picture is where the problematic pump is. So if you look carefully at this visualization, what the visualization does is actually, there have all these black bars, which are roughly corresponding to what we today refer to as histograms. So each of this black bar on this map represent one single death associated with the disease. And then where there's multiple deaths at the same address, the bars correspond to the deaths that are stacked on top of each other, precisely how histograms works. And then where the orange arrow is corresponding to the location of the pump. And then this specific map basically displays observation or insight that all the deaths are roughly clustered around the Broad Street pump, which is the orange pump in the middle of the visualization. So this is sort of one of the first example of data visualization and how it leads to insight and control of disease spreading. Okay. Now, if we talk about data visualization, we have to talk about marks and channels. So we actually have seen a lot of those elements in our first lecture on data visualization, which is, I think it's lecture 13. When we talk about marks, we talk about using marks to try to encode the existence of an item. For example, a row in a table, a data point, right? For example, a point in the scatter plot, a bar in the bar chart, a line in the line chart. The channels that we talk about for visualization corresponding to using position, size, height, and color to encode magnitude or categories of items. And specifically, type of channels, there's different type. You can use channels to encode magnitude. For example, how much data points are there? Where are you can use position, you can use length, you can also use saturation to sort of encode magnitude. You can also use it to encode identity. For example, what item, where the items are, and then using shape, or color, or hue, or spatial regions to encode identity. And then whenever we think about the channels, we need to think about the type of data we are encoding. Either they are categorical, or they are ordinal, or quantitative. And this is directly related to also the color map we're going to discuss very soon. So here are, again, very specific examples of channels, which are used to express types and ranks among the data. From top left, you can talk about sort of channel that using positions among a common scale, or a position with respect to unaligned scales. You can also use length, the angle, the area, and also the depth, especially in 3D situations, the depths to encode information. Then you move on to color. Different luminance, different saturation, curvature, and volume can be used to encode information. But if you actually look at the sort of vertical axis, it's actually an indication of the least effectiveness versus the most effectiveness in terms of communicating the information. For example, the volume is arguably not very effective compared to length and area. Now, you also talk about identity channel, especially when you have categorical attributes. You can use different color and different hues to corresponding to different entities. For example, yellow corresponding to the banana, red corresponding to apple, and so on and so forth. When you have categorical data, you can use color to represent those data set. You can also spatial regions, and sometimes you can also use motion as well as different shapes to encode categorical attributes. So now there's the very important question, because when we talk about visualization, there's entire subfield in visualization that studied this, that's called color theory, that studies sort of how to design the effective color for visualization. So color is typically good for identity channel, but then there is a limited number of classes that you can use color. And typically for human perception, between 7 and 10 color are effective in communicating the underlying data. Beyond that, we are going to lose the effectiveness associated with color. And also it does not work well with quantitative data. Specifically, there's no such thing about, like red in some sense, encode more of my data, or more amount than the green, because there's not really a natural ordering among the data, among the colors themselves, right? So if you think about number 1 is smaller than number 2, is smaller than number 3. Among the colors, people don't have a very good intuition about the natural ordering of the color, meaning that is blue smaller or equal to green? Is it smaller or equal to red? This is not intuitive. So there's a lot of pitfalls in using color in visualization. So the general rule is to minimize the number of color used for encoding the data. And specifically, you want to limit your number of colors to be somewhere between 7 and 10. So specifically, when we talk about color, if you recall, we actually mentioned in the first lecture on visualization, the color map that come out from Color Brew. So a color map basically specify a mapping between color and value. And specifically, in this particular case, I'm mapping the value between 0 to 8 to 8 different colors. And if you're using categorical data set and you almost, for example, if you have a bag of different fruits, you want to use different color to corresponding to different fruit. And specifically, this is what's called categorical color map, because there's not much of a relation among the colors you choose. So that's one type of color. The other type of color is what's called sequential color map. And then there's also what's called divergence color map. So this is sequential, and this is divergent color map. And then and you can also discretize it versus using a continuous color hue. So the idea to increase the expressiveness of color is you want to really map the color map to the different attributes of your data. And then there is actually a very serious sort of investigation into how to choose the right color for quantitative data visualization. And then there's a few typical rules. One is saturation works, but not as well. And try to avoid using different hues, because again, it's not very expressive. And finally, there's actually multiple research papers that is targeting towards a specific danger of using what's called a rainbow color map. So rainbow color map is in a lot of places one of those default color maps. But there's a lot of discussion over the danger of misusing rainbow color map. Specifically, it confuses viewers through its lack of perception ordering, because like what is in front of what is the right ordering for color map. It also obscures data through its uncontrolled luminance variation, and it's actively misleading interpretations through the introduction of non-data dependent gradient. So there is sharp gradient that is created between the color among the rainbow color map that created sometimes misleading information for the viewer. So to give a more example, here is actually a visualization on the left using a color rainbow map, on the right using more of a divergence color map. As you can see, if you look at in the right, you see this particular sort of simulation run, and then you see those nice behavior of the trend of the visualization of the underlying scientific simulation. But on the left-hand side, when you're actually using the rainbow color map, people naturally is driven towards where the hot area or the cold areas are, which are sort of the red and orange area versus the blue area. And they might not be where the features really lie, but the color map, because of the non-uniform gradient, that gradient, that high gradient actually sort of in some way can send a misleading information that those sort of, red and orange area versus the blue area are where you should pay attention to. It may or may not be what the underlying data really is communicating. There's also, and I can't emphasize this enough, is that there is actually quite a bit of color blindness among the population. And then when you design visualization, you have to take that into consideration. For example, roughly 10% of male and 1% of female have color blindness. And then in this particular case, for example, on the lower left corner is sort of the rainbow map when you for normal color perception. And the middle and the right are sort of different color maps that is going to be visible by people with color blindness. As you can see, they actually started missing some of those channels that is encoded by color. Let's just give a specific example. I mean, oftentimes you've seen this color blindness test. Of course, this is a quick test. You probably know by now. If you couldn't tell all the numbers from here, you might have some form of color blindness. Right. So in this particular case, the reason I'm showing this picture is how certain type of color blindness could not differentiate, say, between the color green and then between the color, between red and green, which corresponding to the different hues of red and green. There's a question. Okay, sorry, that's more like a comment. All right. So, when you think about color blindness in visualization, you can actually see a New York Times article back in 2012. It's unfortunately did not take into this consideration, right? So in this particular case, it's happened to unfortunately use a color map that is going from red to green. So if you are not colorblind, you see the differentiation between sort of different groups of the data versus if you are colorblind, there's no differentiation between those groups of the data, which you completely loses sort of effectiveness of your visualization. There's also what's called Stevens psychophysical power law. And then there's a pretty long article on Wikipedia about this. Essentially, the rule is the human's psychological intensity, which what we mean sensation, increases as the nth power of stimulus intensity. So let's look at this plot and give an example. If you look at the blue curve, which is called electric shock, and it has a value of 3.5. What does this mean? This means that, when you accidentally stick your finger into the outlet, it's going to create a very huge sort of sensation, because that sensation or the psychological intensity is to the power of 3.5 of the stimulus that you just received. Similarly, if you think about saturation, that power is 1.7. If you're looking at things like in visualization, when you look at area, their power is 0.7. And if you're looking at, say, brightness in the visualization, that power is 0.5. Okay. So in a way that if you actually look at it, roughly speaking, that the lens is in some sense, you react more to lens than, say, to brightness. So let's do a very quick quiz. If you look at bar A and bar B, how many times is B with respect to A? So you can unmute yourself. 1.5 times, twice, 3 times, 4 times. Anyone? Okay, most people says 2 times. Good. The answer is 2 times. Okay. Now this is more respect to length. Now in this visualization, how many times? Okay, so there's people who say 3 times, 4 times, 5 times, 3.5 times. Okay. It turns out this is 4 times. All right. So you can see that even though length may be effective, but only effective in limited situations. So you need to think carefully when the sort of the ratio is increasing, especially when you go, even for this example, when you go 4 times to 5 times, it's no longer effectively communicated to the user. Now, how much deeper? is A, 2 times steeper, 2.5 times steeper, 3 times steeper, 4 times steeper, 5 times steeper? Any guess? All right, so I get a wild set of guesses: 2 times, 3 times, 4 times, 6 times. The answer is roughly 4 times. Okay, so again, giving this example, the divergence of your answer is an indication that if I want to sort of encode proportion, using the steepness of the curve, the line is not very effective. Now, let's ask the next question. How many times is B with respect to A? 2 times, 3 times, 4 times, 5 times, 6 times, 7 times. Which one? All right, I have a maximum guess of 8 times and 7 times and 5 times. Okay, the answer is 5 times. So again, I just want to illustrate the limit of using size to illustrate the proportion or the quantity of your data. Finally, what about this one? Any guess? It's turned out to be only 2 times. And it turns out it's 2 times diameter and 4 times area, right? Of course, the area is proportional to the diameter squared. So now there's actually a variation over the visual encoding. Do you want to use the diameter to encode the proportion, or do you want to use the area to encode your proportion? So in this particular case, again, you can see this is a situation where you have A and B is only 3 times more than A. But again, that information is sort of a bit not easy to distill. So this example, as we're showing, is actually one of those research area under visualization called perception. So there's actually a large active area where people are looking into what are the most effective visual encodings out there. And it actually boiled down to simple tasks like this. How do I encode my quantities using shape, color, positions, and so on? For example, if I were going to visualize a histogram, what is appropriate sort of the thickness of the bar in my histogram or my bar chart? What is the right spacing, what is the right color, and so on. And typically it's conducted through a user study, which is actually very similar to what we have just done, where I ask a bunch of people to say, hey, if I show you this visualization, can you tell me, is B 3 times of A, 4 times of A, 5 times of A, to see how effective it is to communicate the right proportion. Right, and then the percentage of people who has provided the right answer is, in some sense, sort of the one way to capture the effectiveness of this visualization. Now, let's look at this picture. Can people answer which one is darker, A or B? Right? This is pretty obvious if we're using just shading, and if we only have, say, 2 data items, I can fairly easily to tell the difference between different shades. But what is missing is actually not just which one is darker. I forgot the question. The question is which one is how much darker it is. It turns out this is 2 times darker. Okay. Now, how much darker? Is B 2 times darker, 3 times darker, 4 times darker, or 5 times darker? Okay, so I can't see the chat for some reason. So the answer is infinitely darker. It turns out it's only 3 times darker. Okay, so this leads to another interesting question, is that even though we can tell which one is slightly darker, it's actually not easy for us to tell how much the proportion or the proportion of darkness when we use this. So that is one of those things where if you're using color hues to actually encode quantity, it's not very effective. Now, there's other factors that are affecting the accuracy. For example, things like alignment. If you look at the picture on the bottom, right, I have those two bars, and they are roughly the same length. And the first picture where I'm showing those two blue bars together with those 5 bars. So in a way that the 5 bars are there to, in some sense, distract you, so that maybe you will come up with slightly different conclusion when you are presented with those extra red bars. Now, you can also put those 2 blue bars side by side, but they're actually aligned at the bottom. So if you actually do that, people might argue that, okay, now if I put them side by side and have them aligned at the bottom, then I can actually compare the relative size of this. Now, if you move to the third one, where I don't align at the bottom, and remember, one is slightly longer, the other one's shorter, but I actually just shifted a little bit. And then this is called unaligned. When you do that, it's actually sending a very misleading information because it's no longer easy for a user to differentiate those 2 bars because they are not aligned. So it's actually pretty hard for someone to tell which one is longer. And finally, if you actually move those 2 bars really far away from each other, instead of right next to each other, even though they are aligned at the bottom, you move them really far from each other because of the creation of distances. You are also making it harder to actually understand the actual relative magnitude of those 2 data points. So there's various ways that will, how you position, how you choose color, how you choose hue, how you choose the shape, and how you choose alignment and distances, the scale and distractors to influence the accuracy of your visualization. Okay. All right, so I'm going to move on to design guideline next, but I'm going to give everybody a 5 minutes break. Okay. And we will be back at 4:28. All right, so let's resume. So let's start talking about some general design guidelines. Of course, the whole topic of data visualization, I can spend the entire semester talking about it. In fact, if you are interested in data visualization, there are 3 classes that is offered at the School of Computing. There is the introduction to data visualization, there's advanced data visualization, there's also scientific data visualization. And I encourage you to look into the sort of the courses in the catalog. So when you think about design guidelines, the first design guidelines is rule number 1, use the best visual channel available for the most important aspect of your data set. Okay, so whether the best visual channel is color or its shape or what you can do, but the most important idea, if we go back to the visual channels and the expressiveness of this channel, right here, right? For example, spatial regions versus color, those are more effective ones than shape. For example, length is sometimes more effective than volume. So you want to consider the most effective available channel for the most important component of your data set. And of course, the next one in the guideline, this is just. The second one is the visualization should show all of the data and only the data. So there's 2 components in here. Is your visualization, what we're going to go through is a bunch of examples of mostly ineffective or wrong visualizations or not very good visualizations that you see in practice. But the idea is when you actually visualizing the data, you want to be able to visualize all of the data, not just a subset of it or just chopping off some part of your data without showing them. But also the important part is only the data. You don't want to inject new information in your visualization that is not part of the original data set. There is basically this, what we call integrity principle. And then the first one I cannot emphasize enough is you want to show the variation of your data, not the variation of the design. Oftentimes, students who work on visualization for the first time, or even people who are visualization researchers, sometimes will run into this pitfall of sort of showing the design visualization, is to the design variation. So I can vary a lot of different, fancy encodings for my data. And what people see is a variation of the design, not necessarily the variation of the data itself. The second one is you want to provide clear, detailed, and thorough labeling and appropriate scale. And a lot of examples I'm going to show you today are the ones that failed to give the proper label or scale, and that leads to very misleading information. So oftentimes when somebody give me a scatter plot, my first question is, what is the x-axis and what is the y-axis, right? So by me understanding the label, I understand slightly better of the data. If you just show me the scatter plot without any labeling, it's actually not very useful. The last bit is the size of the graphic effect should be directly proportional to the numerical quantity. So this leads to the discussion of what's called a lie factor. And now I'm going to show you some of the visualization you see in news outlet that has a pretty large lie factor. So the lie factor is the size of effect shown in the graphic versus the size of effect in the data, right? The larger it is, the bigger of lie it is in terms of the lie factor. So it's really is related to what we call graphical integrity, is that the magnitude of your data should be proportional or should correspond to the magnitude of the mark itself. So here is an example. Okay. Can someone tell me what is actually wrong with this visualization? Feel free to mute yourself or put in the chat window. This shows sort of the tax rate between now, or this is sort of old news, between 2 different dates. Okay, so what is wrong with this visualization? Okay, so there's 2 chat, Let's see. One is the difference is small but appears larger because of the y-axis scale. Y scale. Yes, this is sort of not a faithful representation of scale. If you actually look at this visualization carefully, on the y-axis, it initially start with a gap of 2, but it has a gap of 2, but then this visualization is not really showing the right proportion. So in other words, this is actually has effect in data has a factor of 1.14, effect in graphics has a factor of 5, because in some sense, like the light factor in this particular visualization is 4.38. Okay. Now, there's a second one, which is again a scale distortion. Okay. And again, you're kind of distorting the scale to kind of emphasize or de-emphasize the differences between different percentage. Now, this is sort of actually my colleague Alex used this because this is very much German. But what is wrong with this visualization here? If anyone can pick out. And one answer, again, I couldn't see the chat, sorry. It goes off the screen. Yes, that's exactly. So what happened is in this visualization, if you actually look at the last item is 101.7872. It's actually the real visualization should be on the right-hand side, because if I want to present all of the data and to be scale, it actually goes off the screen. So so this is actually, it's not only goes off the screen a little, it actually goes off the screen a lot, right? So on the right-hand side, I think the German means graphic in real, and then one of them is graphic of Crown newspaper. I mean, that's a direct translation of those German words. But this is another example of not presenting the data in the right scale and in a faithful way. What's wrong with this visualization? There's so many things wrong with this. I think Fox News needs to actually at least, this, I don't know which date it is, but they need a better visualizer for their data set. Oh, sorry. It's pretty obvious, right? Is that the actual enrollment and the goal enrollment, one is actually much larger. So in a way that, let me, look at the chat. Yeah, it's not just the wrong value, right? It's also misleading. It's a misleading information. So this would have a pretty high lie factor as well. So, okay, let's move on. There's also the matter when you actually plot the chart, you have to pay attention where is your origin and where is the range of your axis when you actually plot the chart. So you want to use a baseline that shows the data, not the 0 point. So what happened is that sometimes, when your data is far off the screen, that, in a data range, oftentimes, if you're using some of those default plotting tool, it's going to try to also visualize the 0 origin. And then oftentimes what you need to do is kind of reorient or zoom into your data that you want to show, but be very faithful with your axis. And with some time, I also want to start talking about pie chart. I kind of mentioned that pie chart is not very effective. In some visualization, people actually went into extent of writing an entire story about, how I hate pie charts. I mean, I really hate them kind of scenario. The problem is pie chart is, again, a very widely used visual encoding. For example, this is showing the share of coverage on TechCrunch. Okay, so social network is 12%, general consumer 23%, software 8%, and so on and so forth. Then the question is that, okay, what is wrong with it, right? I mean, you've seen pie chart all the time. What is the main issue? Can someone tell me what is the main issue for using a pie chart for data set like this? Any idea? What is wrong? So one obvious thing about pie chart is that it can only show a few categories. Okay, so there's 1, Small slices too small, exactly. So it's not only that, right? If you have, say, all the small slices, 1%, 1%, 1%, 2%, it becomes too small, which means the pie chart have a limited capacity or number of categories you can actually present. But then one of the main issue for pie chart is actually you have limited text. That's good. Yeah. So another comment is that when you put text in there, you don't have too much space for text. But another major issue with pie chart is that it's actually make it very hard for you to compare the actual quantities. So in this particular case, that how do I know which one is slightly better, right? So if I want to redefine it, I can actually use bar chart. Right. In this particular case, I can actually take each of those pie, the corresponding percentage, have this as a bar chart, which is basically left aligned bars. And that provide a much, much cleaner representation of the percentage of each category and how big they are relative to each other. Again, this goes back to the experiment we did earlier about area proportion. Remember, the length is more effective than the area. So in this particular case, if you look at the top two bar, 23% is roughly twice the 12%, right? So when you actually list the left aligned bars, you can roughly capture this proportion, which is the first is twice as long as the second. But if you actually look at the pie chart on the left, that proportion is actually harder to infer from the pie chart. Now, the second thing about pie chart is that it's very hard to actually arrive at comparisons. So you have 3 sets of data. They are all visualized with pie chart, okay? Can someone tell me the difference between those 3 data sets? Like, for example, for, I don't know, for comparison among those 5 categories, what are the distributions? Okay. It turns out this is very hard to do because it turns out those are three different pie charts that capture 3 different data sets. And then those 3 different data sets actually have fairly different distributions. For example, in the first data set, the black bar, which is a black category, has the highest number versus in C, the black has the lowest number. But if you're actually just looking at the proportion of those pie chart, it's pretty hard to understand for a single pie chart what is the relative proportion for different categories, and across the pie chart, how different are the data distributions. Okay. So the question is, what do you want to use instead, right? For example, this is a case, this is a specific case where, let's say you kind of did a summer program project on science aim at improving the perception of the field among 2nd and 3rd grade elementary children. And this is sort of you're showing your data before and after your research, okay? And you're looking at how the sort of elementary students are responding to science, whether they are bored with the science, they are okay with the science, they are kind of excited about science. You're looking at the before and after. If in this particular case, you want to do a comparison, and if you default using pie chart, it's not very effective. But instead, what you can do is you can use what we have before, which is using sort of the bar charts instead of the pie charts. And also the second thing, which is what's showing here, is you are actually combine the pie chart with numbers, which is slightly better, but I would still, which in this particular case is a slightly better, right? But you can also create bar charts that put 2 things together, so you can compare the percentage before and after. For example, before it was 11% bored, after it's 12%. After it's 12%, before it's 40% okay, and after it's 14% okay, and so on and so forth. Okay. So what are the alternatives is to show the numbers directly. So the idea is you show the percentage of increase. So after the pilot program, 68% of kids express interest towards science compared to 44% going into the program. So this is effective. But also, like what I said before, this is the simple bar graph, right? You can look at essentially before, which are in gray, after, which is in blue. So you can actually talk about kind of comparison, but that combined with proper text and labeling, it will highlight, especially here, is say after program, 38% of the children are more excited or were kind of excited, kind of interested and excited about science. Okay, so this way you can actually effectively communicate the research result. The other, excuse me. The third alternative is what we call stacked horizontal bar graph. Remember in the first lecture on visualization, we talked about the options of creating stacked bars. In this particular case, you can, again, using different hues. And, this one also have a little bit issue with the color scheme, but the idea is you can have sort of stacked bars that associate with each of those categories. Okay, but this visualization also have its problem because, again, it's not utilizing the color channel very well. There's also what's called the slope graph, right? Essentially, on the left-hand side, you show the percentage before, and on the right-hand side, you show the percentage after, and you can link the bars. And you can kind of show the trend of decreasing trend and increasing trend. For example, the number of students who are more excited goes from 19% to 38%, which shows a very big, upward trend. And then there's finally a tubular data. When you're thinking about visualizing tubular data, which is actually a lot of data, and then there's actually a particular survey that talk about the visual vocabulary change over time. But when you think about sort of a tubular data set, you need to think about you need to think about the magnitude, distribution, derivation, correlation, ranking, and then time varying scenario. So, for example, when you're thinking about histogram, one of the interesting thing about histogram is you need to start thinking about the number of beings. Okay, so how many beings you want to have, and how to make it and then the solution is potentially making it interactive, so that user might be able to change the beings and so on. The typical rule of thumb is that the number of beings is a square root of your number of data items, or the number of beings is the log of the number of data item plus 1. So here are sort of like typical practice, right? But as you can see in this particular data set, as you increase the number of beings, it actually shows a little bit more sort of detailed trend in the histogram. We talked about histogram before. The second thing we actually talk about is also box plot. The box plot has the idea, right? So if you look at the box plot, the middle line here shows the median, and then it shows sort of the first standard deviation to the left and to the right of the median, and then to the sort of the third and the third of the standard deviation. So the problem with the box plot, even though it's also widely used, it's not very good if you have, for example, a bimodal distribution. So this is assuming you have sort of unimodal distribution. So you also can also talk about median and standard deviation and so on and so forth. But if you have a bimodal distribution, the box plot is no longer very effective. So, so the idea also is that when you actually want to compare data set, you can also looking at, in the first picture, you are trying to do sort of axis aligned bar chart visualization, versus in the middle, you are using sort of the box plot visualization, and then the bottom is actually showing the different distribution. So in this particular case, if you have 4 distribution, one is exponential distributed, one is Poisson distributed, and then the red is normal distributed, and then the green is uniform distributed. You can see how essentially the box plot kind of differ, and then you can see how effective it is. For example, in the exponential distributed thing, when you use box plot, you end up with a lot of outliers, especially when you look at the blue box plot in the middle, that it shows where the median is. But then on the right, because it's exponentially distributed, it has a large number of outliers. Okay, so in a way that this is also indicates sort of the limitation of using box plot. It's only suitable for a certain type of distribution, specifically unimodal, for example, Gaussian distribution. So there's also what we actually have seen in a lecture, the first lecture in visualization using the Jupyter Notebook. We can also see, there is the different plots means sort of dot plot, right? The idea is I want to show each individual data point and kind of want to show essentially the spread of the patient data. So in the middle, you are basically each of this data point corresponding to a particular data point, and we're showing two groups of them. So the better one compared to box plot is actually what we also have seen that we are capable of creating are called violin plot. So on the left-hand side is sort of the box plot look. On the right is a violin plot look. The idea is we are going to use a build on top of box plot. So again, the dotted line in the violin plot is still corresponding to a medium, but then it also takes into consideration of the probability density function of the underlying data point. So this is sort of a comparison between box plot and violin plot of the data set. And then this is actually really fun animation. So what you can see here is that as I am changing the distribution of the raw data set, it maintains the same kind of statistics. So the box plot actually does not change at all. But instead, because the violin plot takes consideration into the data distribution, so you see that as my data changes, it captures more differentiations among more variations among the data set. So it's more effective. Okay. So again, you can actually study different ways to report distribution for experiments, and then this is more useful when you are creating sort of report for a scientific data set. Again, here are different sort of violin plot you can see with different distributions. What we also have studied in the first lecture is how to plot scatter plot matrices, parallel coordinates plots, and for corresponding data. So for example, in here, I have a table on the right-hand side with 4 different columns. Let's say hypothetically, those are the grades of the final for those 4 courses, and each row corresponding to a student. So in the middle, what's happened is that there are 5 rows, which means there's a 5 data point. So when you visualize it, you can visualize each piecewise linear curve in the parallel coordinate plot as a single student. And the position of the sort of each dimension corresponding in the parallel coordinate plot corresponding to the grades of them. So you can actually see in the parallel coordinates plots in the middle, you can kind of see how the students are grouped together. For example, for the subject math, there's 2 students who has a grade of 85 and 90 who are roughly close to each other, versus there's 3 students who are having the grade of 65, 50, and 40, which are roughly grouped together. So parallel coordinates plus is nice because it kind of shows across a fixed dimension how the data along that dimension might be clustered, but it also suffers from the issues that in order to kind of lay out my data, I need to choose a particular ordering of my dimensions. So if I switch the ordering, the parallel coordinates plot will change. So for example, if I visualize first as math, then second as drama, third as physics, and last as dance, then you're getting a different sort of representation of your data, and that has a very different appearance. Now, on the very left, we talk about scatter plot matrix, and scatter plot matrix is talking about sort of correlation for any two pairs of data in there. It's great because it shows pairwise correlation, but it's not great because if you have more than, say, 10 different dimensions, because then your parallel coordinates plots explode in terms of 10 by 10 size. So usually as parallel coordinates plots, is only useful when you choose a subset of the dimensions you want to do pairwise comparison. Okay, so so this is, again, this is what I called about a parallel coordinates plots. The size is d squared, d mean number of dimension, and so on. So it's only useful for a specific a small number of dimensions. And this is sort of parallel coordinates plots, as I mentioned before. Each axis is an attribute, each line is a data item. And this is how you actually, the difference between two data items, one is visualized as a scatter plot, the one is visualized as parallel coordinates plot. And as I mentioned before, the parallel coordinates plot is useful for a tabular data set. And in this particular case, you can see a very nice clustering of data points along, for example, the cylinder dimension, and so on. Okay, so we know that in Panda and Plotly, you can actually come with capabilities of plotting the parallel coordinates plot. And finally, we also want to mention some of those existing other displays, which is what's called pixel-based display. For example, in this particular case, each cell is considered as a pixel, and then the value is encoded through the color. And if you actually use this kind of representation, the ordering is very critical for interpretation. It's actually the same kind of concept when you're ordering also the different dimension of the parallel coordinates plot, which dimension comes first, which comes second. And usually when people do this, they actually use they actually apply some sort of clustering if there's no obvious ordering. And also there is things like heat maps, which we actually have seen before. And sometimes you have to think carefully is whether you are showing sort of too much data set that kind of obscure the information you want to show. For example, this is one example I want to show as a critique, right? This is sort of what I would consider over-designed visualization. This is trying to show the COVID vaccination barriers. I mean, it's so overly designed that is actually missing the main point. In this particular case, probably a bar chart or histogram is better. All right, so I'm going to end today's lecture with an example of Google, and then this unfortunately still carries today. So this is a visualization Google did. They changed back into 2020. Okay, so the top is the old sort of visualization for some of the Google services like Gmail, Calendar, Drive, and Documents, and then Google Hangout. Okay, so can someone tell me what is wrong with their new design? Any ideas? All right, it says too similar. Exactly. So the major critique, unfortunately, they still haven't corrected, is that this is actually the joke. What Google sees is their design, and what average user sees is all the same, right? Color or rainbow scale colors. So there's majorly two things that is wrong with their design, and it's unfortunately still come today, is that specifically in the old design, having distinct color is very important. In the old design, pretty much most of the visualization they created has a distinct color, so they are utilizing the color as one of the most important channel. Okay, remember, shape is not as effective. And what happened is that, not only they mixed all the color, so the color no longer loses its power in terms of differentiating different apps. The second thing is shapes. They all created shape with roughly the same kind of angle. So what happened is that, they no longer have what would call distinguishable shape. So they pretty much screwed up on both fronts in their actually visualization design, that they lost the power of the color channel. They also kind of created shapes that is not distinguishable. So, if after this lecture, if you actually go on news channels, online articles, you are actually going to start kind of seeing those misrepresentation or misdesigned visualization. And hopefully what you learned in today's lecture will be helpful if you were going to design some data visualization in the future. Okay, so that's it for today's lecture. I'm going to stop the screen. So today's office hour is going to be hosted by my TA, Mingzhe, and he's going to jump on soon. Let's see, there's a question. Oh yeah, Mingzhe is here. All right, let me stop sharing.